Welcome to Dr. BT's Chemistry Essentials, A-level chemistry made easy. In this video we're going to look at ionisation energy and how it changes across periods, down groups, and how successive ionisation energies of an element change also. A lot of the ideas are going to link to our previous video on atomic radii and explaining the differences in the atomic radii across a period and down a group. So be sure to have watched that before this video to ensure that you've got those key concepts built up and able to tackle ionisation energy, which is the next step. So firstly, we need to understand what ionisation energy is. Ionisation energy can be defined as the energy required to remove 1 mole of electrons from 1 mole of either a gaseous atom or a gaseous ion. A couple of things to really focus in on here. First of all, it's gaseous atoms are ions, and we're always dealing with 1 mole of electrons and 1 mole of the atoms or the ions. Now, due to this definition, the units are in kilojoules per mole. Now, specifically, the first ionisation energy is the energy required to remove that first mole of electrons from a mole of gaseous atoms. And so if we show this as an equation, and we'll take sodium, for example, then what happens is we take 1 mole of gaseous sodium atoms, and then we ionise that to form 1 mole of its gaseous ion, Na+, with the 1 mole of electrons separate to this. So this is really an oxidation because we've had a loss of electrons from the Na+. And we can visualise this as well from the Bohr model of the atom. So here we have sodium with its proton number of 11, so we know we've got 11 electrons. And then when it becomes the Na+, we remove that 1 electron in the outermost shell. That becomes separate. And so what we've done is we've basically oxidised this to form the Na+. And again, just being really aware of the state symbols. We've got gaseous here, and so we've got our 2 gaseous state symbols on the equation. Now, successive ionisation energies, which we'll be looking at later, is where we have then a second, third, fourth, etc. ionisation energy. And taking second ionisation energy as an example, what happens is the product from the first ionisation energy, the Na+, then becomes ionised once more to form Na2+, plus an electron. And it's a stepwise process. So the first ionisation must occur before the second ionisation can occur. Now, focusing back in on our first ionisation energy here, as this will be where we do most of our work, the ease at which this electron here is removed and ionised links to the amount of energy that's required. So if it's more difficult to remove this electron, then we need to provide more energy in terms of its first ionisation energy in order to allow this process to occur. So the stronger the attraction of the outermost electron to the nucleus gives a higher ionisation energy. And there's 3 things that link to a stronger attraction. And it's all to do with the distance between the outermost electron and the nucleus, with less distance between the outermost electron and the nucleus giving a stronger attraction. Secondly, the number of inner shells that provide shielding. So shielding is where the inner electrons basically take a share of the pull of the positive nucleus. And so the more inner electrons, or the more shielding that there is, then the less attraction that the outermost electron feels from the electrostatic attraction pull of the nucleus. So again, if we have less inner shells, less shielding, we get a stronger attraction of the outermost electron to the nucleus. In fact, if we have less inner shells, that also directly influences less distance, because the more inner shells you've got, the bigger the distance here. And then finally, a stronger attraction will occur if we have a higher nuclear charge, so more protons in the nucleus. And so we need to be able to really understand the idea of distance, nuclear charge, and shielding when we're talking about ionisation energy. What I recommend right now is to pause the video and just turn off the screen and try to recall all of these key concepts, and this includes being able to define what ionisation energy is, specifically first ionisation energy, and then also being able to explain with these three factors how that affects the ionisation enthalpy. Okay, so we're going to apply these ideas to our first set of data here. And what we're going to be looking at is the first ionisation energies across a period. And the period that we're going to be focusing on is period 3. So sodium going through to argon. Now you can see that the general trend in terms of the first ionisation energy is that there's an uphill increase in the ionisation energy as we go across the period. And this general trend is due to the proton number as we go across the period here. As we go across the period, the proton numbers change as shown now. So we have an increase in the proton number, which leads to an increase in the nuclear charge. This increase in the nuclear charge then means there's more positive charge in the nucleus, and so it has a strong electrostatic attraction to the outermost electron. So it decreases the distance between the outermost electron and the nucleus. And so this increase in nuclear charge and its effect on the decrease in distance means more energy is required to remove this outermost electron from the atom. And so overall we can see that these effects here are leading to an increase in the electrostatic attraction between our outermost electron and our nucleus, and so we have a rise in the first ionisation energy because we need more energy to overcome this attraction. Now some of you might be wondering, well, hold on, what if, because we're increasing the proton number, we're also increasing the number of electrons in our element? And surely this may have an effect on the shielding or the distance. However, because we're in the same period here, these increase of electrons are all entering the third shell, as it's in period 3. And so therefore, because we're not adding any extra inner shells, shielding does not change, neither does the distance between the nucleus and the outermost electron. And so these increasing electrons have no effect on the ionisation energy. So this whole train of thought is not needed in terms of trying to explain this data. And so just focus your attention on this sort of flowchart of ideas and the causal links in order to explain the general trend. Now some of you will realise that actually between magnesium and aluminium here, we see that it doesn't follow the trend, because if so, aluminium should be up here. So there's a small dip there. Furthermore, if we were to look at phosphorus and sulfur, this has the same sort of dip. We imagine that the data should all rise like this. And what we're going to look at now is why both of these two dips give us some evidence about subshells. So firstly, we're going to look at the situation that arises when we go between magnesium and aluminium. So we're going to need to come up with the electron configuration of magnesium and aluminium. We're going to start at sodium first, just so we can see how this is changing. Now sodium all the way through to argon, these are in period 3, so we know that the shell is going to be 3 for the outermost electron. So we've got a full 1 shell and 2 shell, and you can see here it's 1s2, and then because the second shell has s subshells and p subshells, it's 2s2, 2p6, so they're full. And then linking to the last subshell, we've got sodium, which is in group 1, so it has 1 electron in its outer shell. Magnesium is 1 more electron, so it's going to be 3s2. And then now we're going to look at aluminium. Now, you'll notice that actually aluminium is also in the free shell, but it is because the S subshell is complete, the outermost electron is found in a 3p subshell. And so if we draw this using an energy level diagram, we can see that as we add in this electron into our energy level diagram, that we have entered into a higher energy level. And as we enter this outer electron into this 3p orbital, then it has a slightly higher energy than the 3s orbital of the magnesium. So the electron is on average further from the nucleus and also has additional shielding because of the 3s2 electron. And it's these two factors here, the increased distance and the increased shielding, that means electrostatic attraction between this electron in the 3p orbital is less attracted to the nuclear charge. And so this means that you need less ionization energy. And so hence why we see this dip as we go from magnesium to aluminium. So it's proof of subshells, because if we didn't have subshells like the S subshell and the P subshell, then we'd expect to just see that general trend occurring throughout. Now if we focus in on the dip between phosphorus and sulfur, then we will need the electron configurations of both phosphorus and sulfur to compare. And so our electron configuration for phosphorus is as followed. So we've got 3p3 as in our outermost electron. So if we go back to our energy level diagram here and just plot those 3 outer electrons, then they are going to want to be in separate orbitals. This is known as the Pauli exclusion principle. And energetically, it's the most stable arrangement rather than these electrons being put in the same orbital. Now, when we move to sulfur, we are going to have 3p4. And so we have no other option than to put this 4th electron in an orbital that is already occupied by an electron. And this causes this outermost electron in the sulfur to have a higher level of repulsion than were it to occupy an orbital on its own, what we would call a singly occupied orbital. And it is this greater repulsion that makes it slightly easier to remove this p4 electron, hence why we see a dip in the energy required here. So again, this is evidence for subshells and orbitals, because if it wasn't for this pairing of electrons in an orbital, we wouldn't see this dip here. Now, the other situation you might be asked to describe and explain is the first ionization energy down a group. And here you can see some group 2 elements, beryllium going down to barium. And you can see that the first ionization energy decreases in general as we go down the group. Now, the explanation for this has strong links with the explanation in a previous video about atomic radius. And so we're going to use the ideas of shielding, distance, in order to explain this decrease in the ionization energy. Now, as we go down the group 2, the proton number is increasing. We're just going to list these beneath each of these elements here. And with these increasing proton numbers, we also have an increase in the electrons. And it's this increase in the electrons and exactly where these electrons go that explains this decrease in the ionization energy. Now, as we go down a group, what happens is the number of shells increases. Beryllium, for example, is in period 2, magnesium period 3, calcium period 4, strontium 5, barium 6. And so in terms of the shells that it has, each period tells you the number of shells. So their overall structure looks like so. And so you can see the number of shells increases as our proton number increases. And more importantly, it's the inner shells that we're interested in. So here we've got one inner shell and one outer shell. Two inner shells, three inner shells, four inner shells, five inner shells. Now these inner shells increase the amount of shielding, which we spoke about previously, and it also increases the distance between the nucleus and the outermost electron, which is the electron you are trying to remove in a first ionization energy. And it's these two factors that feed into each other that means that the energy therefore required to remove that outer electron, and here with these group 2 elements we're just showing the two outermost electrons, the energy required to remove the first of these outer electrons increases as the nuclear attraction between the nucleus and that outermost electron decreases. And so this flow of ideas is really important in order to understand and explain why this first ionization energy is decreasing, linking to some fundamentals about the electronic structure. Now, one thing to note, even though we're increasing the proton number and therefore we're increasing the nuclear charge in the center of our atoms, this is all offset by these effects of the inner shells. And so this set of ideas is ignored when dealing with this explanation of the first ionization energies down a group. Now at this point, I want you to pause the video and see if you can describe and explain the first ionization energies as you go down a group. And then what I want you to do is to then check your answers by scrolling back into the video. So here we have an exam question that I want you to pause the video now, have a go at it, and see if you can get the correct answers. Okay, so we're going to start going through the answers here. Now, part I here is asking you to add a point for an element with the atomic number of 10. Now, what's shown on the graph is atomic numbers 11 through to 18, which you're told is period 3. So 11 being sodium and 18 being argon. Now, Z10 is going to be in period 2, and it is neon. So if we quickly just sketch the shell configuration, you can see that period 3 here, all of the electrons are in the third shell. Now, with neon being in period 2, that means the electrons are in the second shell. So as a result, we would have decreased distance, because the second shell is closer to the nucleus. It would have decreased shielding, because there's only one inner shell. And therefore, these culminate to form an increased nuclear attraction between the nucleus and the outer shell of this neon. So therefore, with this increased attraction, it's going to require more energy to undergo first ionization relative to period 3. So we imagine when we plot this data point for it to be a lot greater than 1500, because period 2, all in all, would have a lot greater ionization enthalpies. So you can see here, 2000 is quite a reasonable suggestion because of this explanation. Part 2 is asking us to estimate the energy. Now, we've been given some data here, and it's asking for 1 Na plus from 1 Na. So you need to know that an Na, the gaseous atom of sodium going to Na plus gaseous ion, is a first ionization enthalpy. We know that the atomic number for sodium is 11. So this is our energy here for the first ionization, so 500. But you'll notice the units of this is kilojoules per mole. We've been asked to estimate the energy required to form 1 ion from 1 atom. So what we're going to do is take this 500 kilojoules per mole and divide it in order to get it for per atom. Now, the thing that links a mole to an atom together is Avogadro's constant. So we're going to take this number, divide by Avogadro's constant, 6.02 times 10 to the 23, and then that will give us the energy per atom. So we take that 500, we divide by Avogadro's constant, Na. This is found on your data sheet, so you don't need to worry about learning that. And then when you do that, you get the answer 8.3 times 10 to the minus 22. And it's such a small number because it is per atom. Now, part 3 is asking us to explain this general increase across period 3. And so this links back to what we've talked about earlier in the video. Hopefully you've included 3 points here. Firstly, the increase in nuclear charge on going from sodium to argon. This increase in nuclear charge then decreases the distance. You could also definitely comment on the fact that there's no change in shielding because all of the electrons are entering the same shell. And then finally, you need to make a comment on the idea of the attraction between the outer electron and the nucleus being increased because of this increasing nuclear charge and decreasing distance for that final mark. And then part 4 is explaining why the general increase in first ionisation energies across period 3 is not followed for magnesium to aluminium. So again, we need to understand that the atomic number 12 is magnesium and 13 is aluminium. So we're focusing on this area of the graph. And you need to be able to explain this in terms of the fact that we are changing the subshell. In magnesium, we are in the S subshell and we have 3s2. And so we're removing an electron from the 3s subshell. Whereas in aluminium, our outermost electron is in the 3p1. And all that we need to then comment on is the fact that the 3p subshell is higher energy than the 3s subshell, and therefore that electron being in a higher energy environment means it requires less energy than expected to be removed. And you can see how the ideas we've been talking about in terms of ionisation energy can be applied to these types of questions. In this video, we've had a big focus on first ionisation energies, looking at the trends across the periods and down groups, and used explanations of attraction, nuclear charge, and atomic radius in order to explain these. In the next video, we're going to be looking at successive ionisation energies and explaining the information that we can get from those. All that remains is that if you found this video useful, that you like the video and that you subscribe to the channel so that you get all the updates as and when they come.